So the key element is really here that you can interactively explore these devices and learn about them. So that gives you a little bit of an idea of what NanoHub allows you to do. And most of our tools are like that. And I want to put this into contrast what most people consider web development of, or web deployment of tools. And we had done this. We started this at Purdue at 1995 with a system called Punch, Purdue University Network Computing Hub. And that was developed at a time where there wasn't even an Apache web server available, right? So they had to write their own web server to do this. And they developed these forms where you can hook in tools that can be launched on remote Unix machines. And that was quite fancy at the time. And the way it works is you fill in this web form, and then you get to this page where you submit a run, and you click on this refresh button, right? Are we there yet? Are we there yet? And what you see once you're there is you get a file browser, and you can look at some files, and you can look at data files or GIF images. So here's a static GIF image. Well, try to zoom into that. Try to compare that to something else, right? You can't do it. You'd have to download the data on your own machine and put it in your own plotting package, and you can't really ask what-if questions anymore as easily. If you look at another output file, you can get something like this again. But at the end is, you ask yourself, what was my input, right? You lost the connection to what was your original question. Did I enter these things right? And that's a typical symptom of no visual feedback and no interaction. Okay? It's really something that is more powerful than not having the tool at all, but it's not very user-friendly either. And the point is, you still have to be a computer geek because you have to download your own stuff in your own visualization engine as well. So to make a case in point, we had Shred, a tool developed by Dragica Veseleska, since before January of 2001. And you roughly see ballpark 10 users monthly using it, and then a couple of poor suckers using it in a classroom. Those are these spikes, where somebody decides, I'm going to use Shred for teaching of Poisson-Schrödinger equation. And I say poor suckers because they didn't come back, right? They didn't decide, well, this is a cool tool, it's going to change my life and my research, and I'm going to do this, right? Then you see a sort of a phase change, like a growth of a factor of 6 or so, 5 or 6. And that coincides with a conversion of these web forms for this tool into something interactive that I just demonstrated. Okay, nothing else. We didn't change anything else. But we increased the usage 6-fold. And what's even more striking is we had before about 10 people downloading the source every month because they said, well, let me just try to download it and install it myself. You could still download it after the Rapture version was there, but people weren't that interested anymore in downloading the source and installing it and maintaining it and compiling it and figuring out how to use it. So really powerful graphical user interfaces matter. Okay? It's not a matter of just, all right, I'll put my stuff out there with a tarball, go ahead and download it. Okay? If you want to make your stuff useful, you ought to spend a little bit of time of making it useful. And we basically think that users really don't want to download and install software. That's the proof. And we see that with most of these apps that we did the conversion in. So the same behavior was seen across all similar converted tools. So to give you an idea of how this system works, I'm going to show you a system architecture of this. So from the outside, nanohub.org looks just like a normal website that has a content management system. But if you go into a tool page where you say, okay, I want to launch a tool, what happens is a virtual machine on top of a physical machine gets allocated, and in that virtual machine we run a Unix application, a full-fledged Unix application with a real user interface, and we pipe that interface to the user into the browser. So it's kind of like a remote desktop or VNC. If these things mean something to you, that's fine. If they don't, then consider it magic. Well, the good thing is now if you run, all this authentication has been happening through this Maxwell's daemon. Now if you run a simulation, it could run in this virtual machine, if it's a lightweight application. But if it's a heavyweight application, it could go to a grid environment where these jobs could be launched on some remote machines. And all the authentication already has happened, right? It's behind the system, right? You don't have to have your own grid certificates and user certificates and MPI commands and SSH commands as a user. It's completely transparent to the user. Now, XY plots and simple plots are actually also delivered from this virtual machine. But if you want to have fancy graphics like 3D rendering of what I had demonstrated earlier, we have a visualization engine that sits in the back, and we pipe the data into it. And when I interact with these 3D rendering images, I actually interact with this visualization engine we call Nanoviz. We have 3D volume rendering in there, and we can do PyMol, like molecular modeling as well, and just pipe the data to this rendering engine and then pipe that, the output, to the user. And again, the user would be interacting with a rendering machine that sits somewhere in the world. Okay? It happens to sit at Purdue. So the problem with scientific computing is not only the creation of the core engine, but the normal process is also that something gets created by a PhD student, and that one PhD student can use it, and maybe the advisor can use it, maybe, and that's it. There's a sort of a cruddy input deck, right, that is not documented, and there is no user interface to speak of, right? You dump out the data in some arbitrary format and you put it into MATLAB or Origin or XMGrace, whatever your favorite plotting package is, and that's it. And so typically there is no user interface, but if you really want to make your stuff useful to others, they have to have an interface. And that is where Rapture comes into play, where you can, it was created at the NCN in November 2004. It's an open source package, and it can work as a desktop application, and it can work for NanoHub. And what it does, it really puts a wrapper around your simulation code, and you can write a sophisticated graphical interface like this that takes literally an undergraduate student 2 days to create. It's actually very simple. And what's really cool about it is we're not asking you to rewrite your simulation code in Java, right? Which is in general a ridiculous thing for some people to ask, where they say, well, if you want to deploy on the web now you got to rewrite your code. That's pretty pathetic. So you can, if you wrote your code in C or Fortran or MATLAB or Python or Perl or Tcl, Rapture will work for you. You don't have to rewrite anything, which is quite a powerful thing. And that really allowed us to enable scientists and engineers like you to develop their own graphical interfaces. It's not that we are in the process of, well, now your boss said, well, you got to put this on the web, now you got to hire a web developer that puts PHP wrappers around your code or rewrites your code in Java. You can leave it as is, as a Unix engine, put an interface on top, and then deploy that Unix engine. It's very powerful. And we have now over 140 tools online. And what I want to drive home is that most other science gateways that I'm aware of say, well, I have this tool, now I want to web deploy it, I got to rewrite major chunks of it, so I need 3 full-time employees for, say, 3 years to do that process. That's 9 so-called FTE. I can guarantee you that as a center, we don't have 9 FTEs for all of these 140 tools, right? So we're doing something radically different. All of these tools are interactive. You can rotate molecules around, or you can look at nanowires, you can look at DFT type calculation or molecular dynamics calculations, or you can look at MOSFET simulations. So it's a broad variety of tools out there.